my paper. All right, I expect everybody to know the difference or how to draw some of the Lewis dot diagrams of the covalent compounds. Take out a piece of paper and draw for me water. Don't look at your previous drawing. See if you could do it by yourself. Draw water. Stress enough that you must be able to draw. Most of you could draw the water. Okay, here's water. This is what it's going to look like. H and H. The carbon dioxide is a little bit harder. You have to know how to draw carbon dioxide. It's going to look like this. It has two sets of double covalent bonds. Whoa, blurry much. We got a double covalent bond here. We got a double covalent bond here. You could draw it with the lines as well. Make sure you have 4 dots on those oxygens on the end. Okay? Let's talk about now, this is new. Okay? Let's talk about the bond versus the molecule. So this is a bond. What kind of bond is it? Covalent. It is a covalent bond. Is that covalent bond sharing those electrons equally or unequally? Say it again. Try again. Unequally. Now, why are they sharing those bonds, those electrons unequally? They are right now trying to, let's get rid of this for a second. Let's move that. They're fighting over these electrons. Okay? Who's winning the fight? Oxygen. Why do we know oxygen is winning the fight? Well, oxygen has an electronegativity of 3.2. I'm going with that. And hydrogen has an electronegativity of 2.2. So when they fight over these electrons, the electrons are just slightly closer to the oxygen than they are to the hydrogen, which means the oxygen is slightly negative compared to the positive. Now notice that I'm putting the negative and the positive in a circle. When I do that, that means slightly negative and slightly positive. Not like when I put oxygen with a -2 charge. So, every once in a while you're going to see it with a little plus with the circle and a little minus with the circle. Or you might see something that looks like this. That's kind of fun to draw. It means slightly negative and slightly positive. This bond right here is called a polar covalent bond. Polar because it has a positive pole and a negative pole. It has a north pole and a south pole. It has a positive, it has a negative. It is a polar covalent bond. So now, I don't know if you still have your little drawing, but you have to have this. So let's put this on a separate piece of paper or whatever. And you'll remember that this is 1.7. And anything up here was ionic. This is the electronegativity difference. And anything below it was covalent. Remember that? Karen, put your phone away. Okay. And when you get up here, you become more ionic. And when you get down here, you become more covalent. And I showed you how you could figure out of all of the compounds that you have, if it is more ionic or less ionic, or if it is more covalent or less covalent, by subtracting the electronegativity differences. Does that make sense to everybody? Do you understand? Okay? Now we're going to talk about the bond polarity. If you are down here where your electronegativity difference is 0, you are going to be non-polar. that means the electronegativities are the same. For example, hydrogen to hydrogen, 2.2 and 2.2. If I subtract those two, I'm going to get a non-polar covalent bond. They are sharing the bond. That's what covalent means. They are covalent because it's less than 1.7, and it's 0 for its electronegativity difference, so therefore it is a non-polar covalent bond. It really goes to like 0.4 electronegativity difference, but the regions will always be 0. On regions level chemistry, it will always be 0 for its non-polar covalent bonds. So all of your diatomics, H2, Br2, Cl2, F2, etc., are all going to be non-polar covalent bonds. This, however, is between two different elements. It's covalent because the electronegativity difference is less than 1.7, but it is not 0. So it is going to be a polar covalent bond. So from here to here is going to be nonpolar. Again, for us it's just 0. And anywhere between here and here is going to be a polar covalent bond. You're going to remember this because the bond, and again, I'm talking about a bond, so just this, is between two different elements. These are not the same, so they are asymmetric. Do you know what symmetry means? It's the same on both sides. If I look at H2O, the H and the O, just that bond, is that symmetric or asymmetric? Asymmetric. If it is asymmetric, that's the A in SNAP, then it is polar. If it is symmetric, like H going to H, symmetric, it is going to be nonpolar. So let's write that down. Symmetric is going to be nonpolar. Asymmetric is going to be polar. The closer you get to 0, the more nonpolar you are. The higher your electronegativity difference is, the higher you go, the more polar you're going to be. Are ionic bonds polar or nonpolar? They're polar. They're really, really, really polar. They're so polar we don't call them polar anymore. We call them ionic. Okay, it's just a way of saying we've got something that's really, really, really polar. You get more polar this way. More polar. Even though they're not covalent anymore, they are still polar bonds. Do you understand that? So look at the bonds between C and H right here. Look at this bond. Is that bond polar covalent or non-polar covalent? Polar covalent. So let's do orange. This is a polar covalent bond. What about this? Whoops, get rid of that. This bond right here. Non-polar. Is it covalent or ionic? Covalent. It's non-polar covalent. Right there, this bond. Let's highlight it. Okay. What about this bond right here? I'm sorry I did not write the H's in for you. There's H's here. This bond right here. Polar covalent. Because it is asymmetric. Okay? Do you understand that? Because I'm going to move on. Alright. Here's water. This bond right here. That bond. Polar or non-polar? Polar covalent. this bond right here, polar covalent. Okay? When you have to watch the semantics that they use. Okay? I have just used the word bond. When we talk about bonds, we are only talking about the connection between two atoms. Now let's look at the molecule. When we talk about the molecule, we need to talk about the entire thing. Okay? Did we write down the shapes? Okay. This molecule is what we call a bent molecule. Write that down. It's bent because these two non-bonding pairs of electrons, let's pull this up. Okay, in the next couple of days you're going to be playing with this website. Okay, let's look at this molecule. Let's clear everything. Move on. This is your central atom. Let's build water. Okay, if I put a single covalent bond on this, this is in a straight line. That's called a linear molecule. If I add another one, it looks like it's in a straight line. However, when we look at water molecules, you see how there's two non-bonding pairs on there? Okay, that's this lone pair. If I add a lone pair, watch what happens to these two atoms. What happened to them? They got squashed because this right here is taking up space. Now we know that a water molecule has two lone pairs, so let's put them on there. Okay? And now we get to look at it in 3D, what it would actually look like. If I take the non-bonding pairs off, just so you can't see them, they're still there. Okay? Look what shape this molecule looks like. Do you see how it's got a bend in it? It's bent because it has these non-bonding pairs of electrons on the outside over here. Understand? So water is a bent molecule. Please make sure you star that. You need to know water is a bent molecule. Because water is bent, and it's bent because these two non-bonding pairs of electrons are pushing the hydrogens down towards each other. Is that molecule symmetric or asymmetric? Okay, let's take a look. What'd you say? Say it again. It is asymmetric. Good. Now, when we test for symmetry, okay, we're going to divide it down the middle. So there it is. Left side and right side are not the same. The problem with doing symmetry this way is you have to make sure that you do it in both directions. Top to bottom, so left and right, and a horizontal line, top and bottom. Check both ways. If it is asymmetric either way, then the molecule is asymmetric. So now we know that this molecule is asymmetric. We're going to say that it has an asymmetric distribution of charge. What the heck does that mean? It means that the electrons are concentrated on one side of the molecule compared to the other. This molecule, the electrons are all concentrated on this side, right here. I'm going to draw this bigger. Here's an oxygen. Here are your non-bonding pairs of electrons. Here's your bonding pairs of electrons. This has an H, this has an H. We know that this bond right here, everybody focus, this bond is polar. It's polar because the H is 2.2 and the O is 3.2. So the electrons are a little bit closer to the O than they are to the H, which means the negative is a little bit closer to this side than it is to this side. And this is happening in this bond as well. The electrons are a little bit closer to the oxygen than they are to the hydrogen. Now, if we look at the molecule, the whole molecule, you can see that this side of the molecule has the positive side, and this side has most of the negative. Do you understand why, Ava? Because the electrons are being pulled this way. The oxygen is stronger than the hydrogen. So this side of the molecule is slightly negative, and this side is slightly positive. New paper. Draw this. H, O, H. Draw that, and put a negative with a circle on that side. That means that side is slightly negative, and this side is slightly positive. So the water molecule is a polar molecule because it has a negative side and it has a positive side. You're going to remember water is a polar molecule because polar bears swim in water. In ice, is that what you said?
Apple juice.
In apple juice. Apple juice is mostly water, so I'll take it. Polar molecules have an asymmetric distribution of charge. They have one side that is mostly negative or slightly negative, and one side that is slightly positive. The bonds are also polar. Where's my highlighter? This is a polar covalent bond, and this is a polar covalent bond. But notice that I'm using different words. Polar bond, polar bond, polar molecule. See the difference? The molecule is the whole thing. The bond is just between two atoms. All right, what about if I drew this now? H, 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 H. That's methane. You've got 4 bonds in there. You've got a bond here, 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 and here. Look at one of those bonds. Is that bond polar or nonpolar? Remember SNAP. Okay. Is this bond polar or nonpolar? Is the bond symmetric or is the bond asymmetric? It is asymmetric. So this bond right here is a polar covalent bond. This is also a polar covalent bond. This is also a polar covalent bond, and that is also a polar covalent bond. However, look at the molecule. Come on, go away, highlighter. Can you go away? There we go. Okay. Look at the molecule. The molecule is the whole thing. Is the molecule symmetric or asymmetric? It is symmetric. If the molecule is symmetric, it is nonpolar. Excellent. Nonpolar. So watch the words that they use when they ask the question. They might say, this is a very famous question, popular test question. Which of the following molecules has polar bonds but is a nonpolar molecule? This one, polar bonds, nonpolar molecule. This one, what kind of bond is this? It's a double covalent. Is it polar or nonpolar? Polar. What about the molecule? Is the molecule polar or nonpolar? Nonpolar. Okay, so this one also has polar bonds, but a nonpolar molecule. All right, that's why drawing them in the shapes is so important. Water is polar. Carbon dioxide is non-polar molecule. Whoops. Molecule. How do you spell molecule? Water is polar. Carbon dioxide is non-polar. What's the shape of this molecule? Everything's in a nice straight line, so it is linear. It is a line. All right. What are some of the other ones I had you draw? Ammonia? Yes? Come on, wake up, guys. I know it's like a Monday, Tuesday morning, but here's ammonia. Okay? Is that bond, and there's a couple bonds here. There's one here, there's one here, and there's one here. Polar or non-polar bond? Polar bond. What about the molecule? Polar. It is asymmetric. It is a polar molecule. Remember when we test for polarity, we're going to split it in half? Oh, it looks like it's symmetric. Nope, you got to split it in half both directions. Okay? Let's look at what this looks like if I were to do this. I'd have 1, 2, 3, but I have a lone pair of electrons. Whoops, I got to show them. And I put it on there. Now look at what it looks like. Okay? In 3D, this side of the molecule is different than this side because this non-bonding pair is still taking up room. All right, what shape is this molecule? Let's look at it. What does it look like to you? Say it again, louder. Triangle. Good. This is called a trigonal. It's a fancy way of saying triangle. Trigonal molecule. It is trigonal. Ammonia is trigonal. It is also a polar molecule. And it has polar covalent bonds. All right, last one. Actually, I already drew it. It's right here. This one, right here. Okay. This is methane. That's the common name. Okay. Is that molecule polar or non-polar? Come on, hang in there. Is it symmetric or asymmetric? It is symmetric. So it is a non-polar covalent bond. I mean, non-polar molecule. Sorry. With 4 polar covalent bonds. Polar covalent bonds. All right. Now we got to get a shape. We have 4 shapes. Linear, bent, trigonal, and then the last one. This one is the one that they will probably ask you about. It is called a tetrahedral. Tetra means 4 around a central atom. So if you have 4 things around a central atom, it is going to be tetrahedral. Let's draw it. 1, 2, 3, 4. That's what it looks like. Okay, so let's look. What shape would this be? Linear. Okay, it's in a straight line. Any 2 atoms is going to be linear. As long as there's no lone pairs, it's going to be a straight line. If there's a lone pair, let's say I do this. Okay, if there's a lone pair, that lone pair is going to take up, and now it's going to be bent.
No, I was just asking why are there like 2 and 3 bonds?
Oh, double covalent bond, triple covalent bond. That's it. So if I do this, What molecule is that? You only know one molecule of two atoms with a triple covalent bond. Nitrogen thingy. What about this one? Oxygen thingy. All right, if I go back to this, okay, there's carbon dioxide, linear molecule. There's no non-bonding pairs up here. If I do ammonia, it's going to look like this. Here's the non-bonding pair of electrons, and here are the three. That's trigonal. Can you see the triangle there? CH4, what's the shape of this? What's the shape of that? It's got 4 atoms around a central one. Tetrahedral. What's the shape of this guy?
I don't know.
Yes, you do.
Looks like a
Trigonal, good. What about this guy? Linear. See them right here? They're all in a straight line. There's got 3 non-bonding pairs, but they're all taking up that space. Some of these are more complicated than we need to know. Oh, sulfur dioxide. Bent. Because this non-bonding pair pushes these two towards each other. Okay? So, recap really quick. Okay? Water is a polar molecule. Remember, polar bears swim in water. It is bent. Carbon dioxide is a nonpolar molecule. And it is linear. We've got CH4, which is a nonpolar molecule. And it's tetrahedral. And we've got NH3, which is a polar molecule. And it is trigonal. Any questions on that? Polar bond, polar molecule. Most important one, water. Water is polar. Did I say water is polar? Water is polar. It has an asymmetric distribution of charge.